In this video, we're going to take a look at example number 5. And I'm actually going to have you do most of the work on this example because I want you to make sure that you're practicing these ideas. So I'm going to ask you to pause the video and try to work through this in just a moment. But here's what we have. Suppose that C1 is given by R1 and C2 is given by R2. Notice these are kind of the same functions that we started with at the beginning. We're still going to be dealing with starting at 0, 0, and going out to 1, 1. And we either have a line to take us there, or we have this kind of parabola path. But notice that I have changed the vector field. I've changed the vector field to be y squared, x squared. And so what I would like you to do is try to go through and actually compute these two line integrals, and then see if you can answer part C. And then we'll go ahead and try to collectively tackle part D together. So I'll ask you to pause the video here, and when you're ready to see the first 3 parts, you can unpause. All right, so I'm going to go through and actually set this up. It should actually be fairly simple. Let's see. I know that when I integrate here, I can re-express this as an integral from 0 to 1, and I'm going to have an f dot dr. So that's a y squared, x squared, and dotted with my dr, which is my dx, dy. Now I just need to make sure that I convert all of this over to t values, so I can actually work with everything that I have here normally. So I'm going to rethink about this as, if I'm integrating from 0 to 1, y squared is the same thing on C1 as t squared. The other one here is also t squared. And then when I deal with my dx, I know this is going to be 2y dy. Oops, sorry. That's the wrong value. When I deal with the derivative of my x, that's going to be 1 dt, and the other one's also 1 dt. So this is really just going to be the integral of a 2t squared dt. This is a 2/3 t to the third evaluated from 0 to 1, and I get 2/3. Now this is at least one way to think about doing this calculation. In this part B, I'll do the calculation in a slightly different way that's equivalent. So here, I'll think about replacing this again with something that we did in the previous section, which is I'll take my f and evaluate it at that value of r, and then I'll dot it with my r prime of t, and then put my dt at the back. What you'll notice is that I'm going to get the exact same sort of construction that I did up above. This time, though, I'm using the values from R2. So I'll see that if I take my y value, which is t squared, and I square it, I'm going to get t to the 4th. If I take my x value and I square it, I'm going to get t squared. When I set up my r prime, I'm going to end up with a 1, 2t, and a dt at the back. Notice I got the same thing kind of up above. I just had my dt inside of this, and you could imagine factoring it out. Or not factoring, but undoing the scalar multiplication. Now here, I'm going to get down to an integral that's from 0 to 1, and I think I'm going to end up with t to the 4th plus 2t cubed and dt, and I want to evaluate that. So that looks like 1/5 t to the 5th plus, I guess that would be 1/2 t to the 4th if I simplify. When I evaluate from 0 to 1, I'm going to end up with 1/5 plus 1/2, which is also known as 7/10. Okay, so we calculated these two things, but why? Well, here's the important question on part C. Is this line integral here, or this work integral, I should say, independent of path in 2 space? And immediately I should be able to answer that question as no, because if it was independent of path, I should have gotten the same answer when I went from a common start point to a common stop point. The path I take to get there shouldn't matter. So we can say here no, taking 2 different paths from 0, 0 to 1, 1 produced different results. So there is no way this is independent of path. Now, part D then becomes the important thing to consider, and it's related to the theorem that we had at the end of the last video. Is the above vector field then actually conservative? And if we take a look back at what we saw in the last video in this important fact, we said if a vector field was conservative, then it was definitely independent of path. But we also saw this. If a vector field is not independent of path, then F cannot be a conservative vector field. So here I can say that since this line integral or work integral is not independent of path, we know that F is not conservative. So this idea is really powerful. It shows us how we can actually demonstrate or prove that a vector field is not conservative. Okay. Of course, what that means is that if it's not conservative, it would be, as I state here, impossible to find a scalar function whose gradient comes out equal to this value of f. Like you could try for the rest of eternity to come up with a little f whose gradient equals this. But what we've been able to discover is it's not possible. No such function exists. Don't even bother wasting your time looking for it. So this is a really, really cool result. In the next video, we'll take a look at some new definitions and results dealing with independence of path and conservative vector fields, and try to take a look at some of the things that we can conclude after we introduce these new ideas.